Welcome to the third and final lecture video in this first class time series of lecture videos. I guess you've made it to the last video for this first class, which is great because here we're going to shatter the myth of resonance, right? I love destroying the little lies that we tell ourselves to make the world make sense with, a deeper view of what's going on. So the molecular orbital description, something we, talked briefly about in the first semester of organic chemistry, and we'll revisit it. If you recall ethylene from that first semester of organic chemistry, we had, a double bond, right? Which is this pi bond composed of two p orbitals. I have not, shaded one of the lobes. And of course, our carbons are both sp2 hybridized, right? They're trigonal planar. And what is, a crude molecular orbital diagram for this, ethylene? Well, we talked about it. We said, we know we have 4 carbon hydrogen sigma bonding type molecular orbitals. And if we have that, we've got 4 carbon hydrogen sigma star antibonding molecular orbitals. These are low in energy and these are high in energy. Why are these low in energy? Because, we've got a carbon sp2 overlapping with a hydrogen 1s. And that energy combination is going to be lower than, say, our sigma carbon-carbon molecular orbital, which is composed of a carbon sp2 overlapping with another carbon sp2. So sp2 is a little higher in energy than an sp2 1s combination. And of course, I think we all agreed that our pi bond was formed by 2 p orbitals that are left over on each carbon, right, to interact with each other and give us our pi bond. And so that pi carbon-carbon bond, bonding molecular orbital, is a little higher in energy still than the single bond component. Because the single bond component, that sigma bond, is made up of an sp2 hybrid overlapping with an sp2 hybrid. That's a lower energy combination than what? A 2p overlapping with another 2p. Why? Because an sp2 hybrid has s character, right? And s, that 2s atomic orbital on carbon is lower in energy than the 2p, right? So you take 2 straight 2p's and those are going to be a higher energy combination than, 2 sp2 hybrids overlapping with each other. So hopefully that explains this sort of energy ordering. And then of course on the antibonding side, well, the deeper your bonding molecular orbital, the higher in energy your antibonding corresponding molecular orbital. So what falls out of this crude molecular orbital diagram? Well, what falls out of it is, our highest in energy occupied molecular orbital, our HOMO, is the carbon-carbon pi bonding molecular orbital. And the lowest unoccupied molecular orbital in energy is this pi antibonding carbon-carbon molecular orbital. So this is the dual face that ethylene presents to the world. If it accepts electrons, it will accept it in the lowest unoccupied molecular orbital. And indeed, if you're a strong enough nucleophile to put electrons in that pi antibonding carbon-carbon molecular orbital, the effect you have is essentially you will break that pi bond. Alternatively, our ethylene can act as a Lewis acid, an electron pair donor. And the easiest electrons it has to give to the world would be the ones that are located in the highest occupied molecular orbital, that is the pi bond. Those are the lowest, least tightly held electrons, the highest energy, and the easiest to, interact with the world. So molecular orbitals arise from a combination of atomic orbitals. The number of atomic orbitals always equals the number of molecular orbitals you have involved. The real area of that molecular orbital diagram that we're interested in is obviously the HOMO and the LUMO, right? Because that tells us what happens to the molecule, how it can react with the world, and the two faces it presents, right? And of course, for the case of ethylene, we were focused in on the, p orbitals that went into making those molecular orbitals. The combination of the two p atomic orbitals gave us the pi bonding carbon-carbon molecular orbital and the pi anti-bonding, the pi star carbon-carbon molecular orbital. And so here we're just looking at the pi system, right? We could either have those two p orbitals combine in such a way that the lobes on the, one side of the plane of the molecule are the same phase, right? And then the lobes on the bottom, the other side of the plane of that molecule, are the same phase. And if they are, they can overlap, and that gives us our pi bonding type molecular orbital, right? Because you can have shared electron density between the two nuclei. Now, if those p orbitals were out of phase across the plane formed by the molecule, they can't overlap, right? Because they just destructively interfere, wipe each other out, and you can't share electron density between those two atoms. We call that the pi antibonding, the pi star carbon-carbon molecular orbital. Now you'll notice, because of the p orbitals, the p orbitals have a nodal plane already, that molecular orbital that is bonding still has a nodal plane, right? You have a cloud of electron density above the plane of the molecule and a cloud of electron density below the plane of the molecule. But once you go up to this anti-bonding, you put a vertical node, right? It's not a horizontal node. You've added a vertical node, and those two lobes cannot now overlap. All right, so let's take it one step further, because we still have 3 or 4 minutes left on this video, hopefully, before I lose your attention. Hope I didn't lose it already. You're surfing somewhere else. The OWL system. Let's look at the 3 adjacent p orbitals on this OWL system, because you've got a pi bond, and then either you've got a radical, a carbocation, or an anion, right, on the terminal carbon. But hey, those are all existing because of a p orbital, right? So you really have 3 adjacent p orbitals, and let's combine them to make 3 molecular orbitals. Well, we'll do so in this linear way, right? Our lowest energy combination of those 3 orbitals is one such that all the lobes on one side of the plane of the molecule have the same phase, and then all the lobes on the other side of the plane of that molecule have the same phase. So there are no nodes, right, other than the nodal plane that is formed by virtue of how p orbitals are. They each have a nodal plane, and so when you combine 3 of them, they have that same nodal plane, right? But there are no vertical nodes in this pi bonding, lowest energy molecular orbital combination of these 3 2p orbitals. We take one step up in energy and we add 1 vertical node. Where are we going to add that? Well, we're going to be rather equitable in our placement of this node. It's going to fall directly over that middle carbon. Oh my gosh, what happens if there's a node that falls directly over an atom? Notice I didn't even draw lobes on that carbon. Why? Because what does that vertical node mean? That means there can be no electron density in that vertical space, right? Which means there's no lobe, no lobes associated with that carbon atom. That's just weird, right? But yeah, we stepped one step up in energy. We got to add a vertical node, right? We call that our pi non-bonding molecular orbital. We symbolize that by, pi NB. It's just that second molecular orbital, right? Each molecular orbital takes 2 electrons. That's nice. What happens if we step up one more step in energy? Well, now instead of 1 vertical node, we have 2 vertical nodes. And again, we're going to be awfully equitable in the way we place them. Now they are across carbon-carbon bonds. And every time you step across a node, you invert the phase of the lobes of the p orbitals. So we call this our antibonding molecular orbital. And indeed, each p orbital on each carbon is acting like an isolated p orbital. Well, what falls out of this? Maybe we'll see a more clear picture when we look at the different types of allylic systems that we can have. We can have an alkyl an allyl radical, and an allyl anion. So let's look at what the molecular orbital diagrams look like for each of those cases, right? Oh my, here we go, right? Here's our alkyl. What is the highest occupied molecular orbital? Well, it's the pi bonding type molecular orbital, where all three p orbitals on all carbons have the same, shading and phase on the same side of the plane of the molecule. What's the lowest unoccupied molecular orbital? It would be pi non-bonding, right? And in fact, the alkyl is characterized by reactivity with nucleophiles, that is, with molecules that can donate to electrons. And that's characterized by the lowest unoccupied molecular orbital, because that's where it can accept 2 electrons. And what does that look like? Let's go back, right? Go back to the top of the page. What does that look like? What does pi non-bonding look like? Oh, there is one node. It falls across the middle carbon. And there are 2 p orbitals, right? One on each terminal carbon. Well, those p orbitals are the places where you can add electron density, right? If you put 2 electrons in the pi non-bonding molecular orbital, they're going to go either at, the leftmost terminal carbon or the rightmost terminal carbon. And that's described by resonance, right? That formal positive is either at the rightmost terminal carbon or the leftmost, right? But it is never in the middle. And indeed, a nucleophile can never add its electrons to that middle carbon because there's a node that crosses it. Isn't that interesting, right? Molecular orbital description of the alkyl basically tells us why resonance is, works as a way of understanding how nucleophiles react with this type of carbocation. They either add to the rightmost carbon or the leftmost carbon, and that's because of the way the pi non-bonding molecular orbital, the LUMO, looks like, because that's where the nucleophile's electrons go. All right, how about the allyl radical? Well, it has a single electron in the pi non-bonding molecular orbital. Why? Because there are 2 electrons in that pi bond, right? And then there's 1 electron in this p-like orbital of this particular resonance form. So that's a total of 3 electrons in our pi system, which is made up of the 2 p orbitals, right? So as we fill that molecular orbital diagram, we put 2 in the lowest molecular orbital, and we have 3 total. So we put our other electron in this pi non-bonding if we have the lowest energy, state of our allylic radical. We call that a singly occupied molecular orbital, a SOMO. And again, the allyl radical has reactivity characterized by the SOMO, which happens to be pi non-bonding, right? And so what that means is that radical, that 1 electron, right, it either exists in this p orbital on the leftmost carbon, or it exists in this p orbital on the rightmost carbon. How it gets from left to right carbon, I can't tell you, right? Because it never exists in between, right? That allyl radical won't react with other atoms on that middle carbon. It either reacts on the leftmost carbon or the rightmost carbon. And that's because of the way that pi non-bonding molecular orbital looks. Isn't that fascinating? It is to me. And okay, what about the allyl anion? Well, we've added 1 more electron, so we've got 4 electrons total in the pi system, 2 in that pi bond, right? And then 2 in this p orbital over here in this resonance form. So 4 electrons, 2 in the pi, 2 in the pi non-bonding. Well, the allyl anion has reactivity characterized by the highest occupied molecular orbital. That is pi non-bonding, right? It does not want to accept 2 electrons. Why? Because it's already got a negative charge. And opposite charges, repel each other. So it reacts as characterized by, pi non-bonding as well. And oh, lo and behold, pi non-bonding. There's a node across that middle carbon. So those 2 electrons are either going to be on the rightmost carbon in that p orbital or on the leftmost carbon on this p orbital. And indeed, that's what we see. So that's molecular orbital diagrams explaining why, our resonance forms are correct, right? That our formal positive on our allylic cation is either on the rightmost carbon or the leftmost carbon, but never on the middle carbon. Same with the radical, and same with the anion pair of electrons. Great, you've made it through this video. I will hopefully see you for the second class time series of videos.